Welcome to Scarlett. Scarlett, which stands for Scalable and Reconfigurable Electronics Platforms and Tools, is an EC-funded FP7 First Call project coordinated by Thales Avionics. This presentation will provide you with a summary on the topic of time-critical aspects on IMA platforms. It looks at what is defined as time-critical and also the considerations for implementing time-critical applications on the IMA platform. First Generation IMA is reviewed, followed by the restrictions when implementing time-critical applications. Following this, IMA 2G is presented, showing how the innovations proposed by Scarlett will enable the more efficient integration of multiple time-critical applications. To begin with, a reminder of some basic terms and definitions which will appear in the presentation and a reminder of the IMA concept. The definitions will include the meaning of time-critical as used in this presentation. Then IMA 1G, its concepts and the issues with TC functions. Next is a summary of the key features of IMA 2G and the TC aspects. And finally, an indication the innovations applied in Scarlett. This slide is to introduce some of the terms or definitions applicable to IMA 1G. Common resources. This refers to the provision of a common LRU, which has the ability to fulfill multiple functions, for example, CPIOM. This is one of the key means to provide a cost-effective avionics solution. AFDX, Avionic Full Duplex Switched Ethernet. IMA Perimeter. This refers to the list of systems which are hosted by IMA resources. CPIOM, Core Processing Input-Output Module. A processing unit with built-in I/O, primarily used on IMA 1G architectures. IOM, Input-Output Module. Additional I/O translation to AFDX, either for direct discrete or analog types, or for a system-specific LRU without an AFDX connection. RDC, Remote Data Concentrator. Within IMA 1G, the RDCs were system-specific, often without an AFDX interface, usually A429 or CAN, and connected to the CPIOM or a system-specific LRU. This is a basic slide to remind you of the IMA concept. Individual LRUs, which perform processing and I/O, are replaced by a CPIOM running multiple applications. If the output of an LRU requires conversion to AFDX, an IOM is used. These two concepts, CPIOM and IOM, were the first steps to provide common resources. The first point to address is, what do we mean by time-critical? Essentially, any event which requires a guaranteed maximum response time is time-critical. This becomes difficult when the required response time is less than 20 milliseconds and maybe as low as 5 milliseconds in some cases. It can also specify a time window, for example 4 to 5 milliseconds, where 3 milliseconds or less is a failure and 6 milliseconds or more is a failure. Therefore, the avionics must support short periods, high rate, must provide low latencies, and must provide deterministic behavior. So what do we need to consider? There are two parameters involved: latency, which is the end-to-end timing and detailed in the next slide, and period, the interval between starting the application. So to look at latency. Latency is the combination of many factors. If we consider time as moving from left to right, we have several activities to consider. The conversion of a sample to AFDX, the transmission over the network, the processing of the data to produce an output, the transmission of the output data over the network, the conversion of the data from AFDX to an analog discrete output, settling time assumed to be negligible. Each of these actions has a minimum and maximum time during which it can be completed. The difference is the jitter. Jitter is the variation in the timing due to the tolerances in the system components, a large part of which is a result of the asynchronous nature of the AFDX elements. The jitter from each action must be combined to determine the worst case. One final consideration is the sample interval. It's important to emphasize that the time window starts at the moment the event occurs, not the moment at which it is detected. Therefore, sampling interval may play a significant role in the overall timing budget. The effect of jitter is one aspect which may be evaluated on the TC demonstrator, as the decision was taken within Scarlett to adopt a fully asynchronous architecture for the demonstrator in order to evaluate its performance under the stringent TC requirements. The period is a function of the system requirements. As the period between the running of an application is reduced, the context switching overhead of the OS consumes a greater portion of the time. This is one aspect which the TC CP/M OS must address. The relationship between the latency and period will impact the performance and efficiency of the solution. If the two are not matched, then the network or the processing will be over-designed. In some cases, however, this may be required to meet system performance requirements. Systems requiring fast time critical functions include braking, specifically the anti-skid function, steering, nose wheel, primary flight controls, high lift, slats and flaps, and cabin pressurization. It is not the purpose of Scarlett to demonstrate all TC functions. It should be noted that this presentation is focused on the time-critical aspects and therefore does not dwell on the scalability and reconfigurability topics within Scarlett. Here we have an example of an IMA 1G architecture, a definition which is a key to IMA and will be used many times is common resources. Common resources refers to a component which can be configured to host a variety of applications or provide a resource to multiple systems, such as the CPIOMs, the Core Processing Input-Output Module. The CPIOMs are dedicated to a group of functions, for example fuel, landing gear, with the I/O adapted to the needs of those functions. The next component is the IOM, the Input-Output Module. If a system-specific LRU or sensor actuator was required to be connected to AFDX, a dedicated LRU, the IOM, was required to convert the output to the AFDX standard. As mentioned earlier, the CPIOM and IOM are two examples of the use of common resources on an IMA 1G architecture. The next component to identify is the AFDX switch. The switches are linked to form the primary data communications for the IMA. The next component to address is the RDC. Within IMA 1G, these were not common resources as the different systems implemented their own RDCs. These had a large overlap in their functionality but were totally different in their design and implementation, with the associated duplication of development, costs and support. The last part of this slide relates to the sensors and actuators. The term raw sensor has been used to differentiate from a smart sensor, a term which will be covered in the IMA 2G slides. IMA1G hosted some, the slower loops of a function, for example breaking command, but not any fast time critical functions. This was due to multiple reasons. CP-IOMs not optimized to efficiently integrate multiple fast TC applications. CP-IOMs tailored for the I/O, not the processing demands. AFDX network optimized for high loading utilization, not low latency. Rapid I/O conversion using RDCs and AFDX was not possible. Implementing distributed architectures may require oversampling to reduce the impact of network latencies. As a result, IMA1G was unable to efficiently host fast TC applications. All time-critical functions were implemented using I/O directly on CP-IOM or dedicated resources with dedicated communications field bus. In addition to being in conflict with the IMA2G goals of separation of processing and I/O, this resulted in a high part number count and multiple types of field bus, A429, CAN, etc., often with multiple instances. If we now start to look at TC functions on IMA2G, some of the goals of IMA2G: host more functions on IMA, reduce hardware part count, increase use of common resources, provide resources for TC functions as common resources, components, and communications, field buses, reduce cost to end customer. As more systems are included within the IMA perimeter, the range of common resources, both processing and communication, increases, but the numbers required for each also increases. The goal is therefore to provide the time-critical functionality using common resources and a limited set of communication types, potentially all AFDX-based. These common resources are required to run fast loop functions, be optimized for low latency and short periods, separate the I/O from the processing to enhance scalability and reconfigurability. This slide is to introduce some of the terms or definitions used in the presentation related to IMA2G. Common or shared resources. As before, this refers to the provision of a common LRU, which has the ability to fulfill multiple functions, for example, a CPM, to use IMA2G terminology. This is one of the key means to provide a cost-effective avionics solution. The new components when compared to IMA1G are the CPM Core Processing Module. This is the main computing resource. LC-AFDX, Low Capacity AFDX. This is a variant of AFDX, optimized for low latency and jitter. RDC, Remote Data Concentrator, provides essentially the same functionality as in IMA1G, but is now a common design. RPC, Remote Power Controller, provides a distributed power switching capability. REU, Remote Electronics Unit, provides input and output and processing for fast control loop hosting away from the main CPMs. Please note, this is often referred to as an IRDC or Intelligent RDC. Smart Device, Sensor or Actuator. Basically a dumb sensor or actuator, but with a digital data bus connection replacing the analog interface. This is a basic diagram on the IMA2G approach. The main AFDX network is similar to the IMA1G. However, in this implementation, some of the AFDX switches may be located away from the avionics bay to simplify installation of wiring. A fundamental difference is the separation of processing and I/O. We now only have CPMs, no I/O, for processing and dedicated but common devices for handling the I/O. The main I/O resource is the RDC. There are different types of RDC with slightly different purposes. The goal is to develop a minimal set of components which will meet all requirements. RDC, Remote Data Concentrator. This is now an IMA resource which translates the bulk of the I/O to and from AFDX or LC AFDX. RPC, Remote Power Controller. This concept provides higher power outputs for driving loads which cannot be driven from RDC. Above a certain power level, extra protection is required, and this impacts the utilization rate of the I/O on the RDC. IRDC, essentially an RDC with the ability to run 2 or 3 applications. The other new concept here is the smart sensor or actuator. Essentially, this is the raw sensor or actuator with added functionality in terms of limited processing, byte, maybe data loading, and a digital data bus link, as opposed to an analog or discrete link. Smart sensors or actuators have a standard interface but may have different implementations. Although this allows components from different suppliers to be used, it does resist the move to common resources. REU. This resource provides closed loop control for a fast response application. The REU has a single application plus housekeeping functions, but can be adapted to multiple uses. The REU is shown as being very close to the actuator. It will also be connected to any relevant sensors. The actual location will depend on the installation constraints. The final part to highlight is the LC AFDX, Low Capacity AFDX. The LC AFDX is proposed as a field bus, either shared between a small number of systems or as a dedicated intra-system bus. It offers the potential for lower latency network communications and is a feature of one of the architecture options of the TC demonstrator. The innovations, compared to IMA 1G, being driven by Scarlett are a dedicated TC CPM designed for a fast response with simple calculations and efficient integration of TC applications and minimal overhead, for example fast context switching. Given the short processing times expected, unless specifically addressed, context switching could form a significant part of the timing budget. The drive is to host all TC functions on IMA 2G using common resources, regardless of required response time. Objective to provide both centralized and distributed architectures with IMA 2G for time-critical systems. Fast loop on CPM with generic RDC using standard AFDX. Fast loop on CPM with generic RDC with low latency field bus communications. Fast loop on generic REU or IRDC. We are also developing implementation and optimum deployment of a low latency field bus compatible with AFDX, suitable for all applications. The ability to host the fast TC applications on multiple components centrally or remotely permits the deployment of a flexible architecture, which is suitable for use on aircraft of varying size, business jet to large commercial, demonstrating the TC compatibility with the scalability aspects of Scarlett, and can be changed at a late stage, for example to accommodate changes to the network without a major impact or significant new development. Other key components used within the TC demonstrator for Scarlett are an optimized subset of ARINC 653 to support the TC applications, ARINC 653 being an industry standard application programming interface. Common Resources (REU) used for closed-loop control, compatible with the TC CP/M to permit applications or functions to be hosted on either increasing architectural flexibility without significant software effort. The basic RDC also requires some TC elements: low latency deterministic I/O conversion, analog discrete to LC AFDX and vice versa. Both AFDX and LC AFDX end systems. Combinatorial logic for simple closed-loop functionality. It is also required that the TC components are able to run non-TC functions without compromising safety or performance. The main limitations for the TC demonstrator are not flight representative, no integrity considerations, no reconfiguration on TC systems within Scarlett TC demonstrator. So, just to remind you, what do we mean by time critical? Essentially, any event which requires a guaranteed maximum response time is time critical. It can also specify a time window, for example 4 to 5 milliseconds, where 3 milliseconds or less is a failure and 6 milliseconds or more is a failure. From the list of typical systems which require time-critical functionality, braking, steering, flight controls, high lift, cabin pressurization, it is intended to demonstrate the first three within Scarlett. So, how do we propose to demonstrate the TC functionality of IMA2G? The TC demonstrator will have three configurations. The switch between architectures 2 and 3 will demonstrate the flexibility of this approach. The next slides will present the architectures. Architecture 1 will consist of CP/Ms, AFDX and RDCs. CP/M runs TC application, RDC manages all I/O, AFDX handles communication. This will be the lowest performance variant to demonstrate time-critical behavior, but not necessarily the lowest latency. This will demonstrate the nose wheel steering application. Architecture 2 will consist of CP/Ms, AFDX, RDC, REU, IRDC. CP/M runs slow loop components, but still TC. RDC, not shown in the slides to improve clarity, handles normal I/O. REU, IRDC, runs fast loop component of the application and handles the I/O relevant to the fast loop processing. This is for applications with high performance, low latency requirements, such as anti-skid. Architecture 3 will consist of CP/Ms, AFDX, LC-AFDX and RDCs. CP/M runs TC application, RDC manages all I/O, AFDX handles most communication, LC-AFDX handles low latency communication requirements. This is an alternative method to implement applications with high performance low latency requirements such as anti-skid. Implementing a distributed architecture for TC functions can provide benefits. For some TC systems, the fast time critical function is tied or linked to a specific set of components in a defined location. For example, the anti-skid sub-function of braking is linked to a specific wheel or pair of wheels and the associated brake components. Providing the ability to run TC applications remotely has the following benefits: significantly lower network loading, communications associated with the slower loop only, improvements in system availability, less likely to lose all components associated with a function. Potential for faster response, and processing on the remote resource allows improved byte. So the question is, which way now? The basic messages today are, we are keeping our options open. Deploy common resources where they provide benefit. Many trade-off studies are being performed, some of which will be answered by Scarlett, some by aircraft-level decisions or market demands. There is no restriction on non-TC systems applications utilizing TC resources. Ultimately, there is no guarantee that a TC CPM will appear in the final solution. If the TC demands of the systems are met most efficiently by using remote processing and low latency networks, it may be that an HP or high performance CPM can meet the required timing constraints. A further push towards common resources. In summary then, fast time-critical TC applications were not practical on IMA 1G. Some examples were implemented, but they did not require less than 20 milliseconds response times. The goals within Scarlett are to demonstrate fast TC applications using multiple architectures. The approach being developed within Scarlett will provide the flexibility to change the architecture at a late stage without significant impact, and the flexibility to adapt the architecture according to the aircraft needs and size without significant redesign of the applications. Thank you for listening. Please visit our website, and should you have any further questions regarding this video presentation, please do not hesitate to contact any of the persons mentioned. Thank you for your attention.